So this is a programming course, not a linear algebra course. But in a programming course like this one with engineering applications, it doesn't take long until we have to do a little bit of linear algebra because we often use programming to solve linear algebra problems, and linear algebra problems show up so much in an engineering setting. So you're not going to be tested on your knowledge of linear algebra terms, but we do need to learn just enough about it that we can do assignment 4, which does cover some basics of linear algebra. So for the sake of this course, we just care about the methods that we use to compute things, not necessarily their mathematical significance. And that means because I really like the mathematical significance, I sort of have to bite my tongue and only talk about how to actually perform operations. So first, a bit of terminology. What is a vector? A vector is a way of referring to a fixed size sequence of values with one name. So this is a vector v that has 4 components. And here we have a vector u that has 3. And normally, especially in a context where we might be mixing together vectors and single scalar constant values, normally it is a good idea to indicate that what you're talking about is a vector by giving it a little hat with an arrow on it like this. So we could say v equals 6, 10, 17, 187. It's a matter of personal taste, I think. There's a long-running dispute about whether we use these little angly brackets or whether we just use round brackets. It doesn't make much of a difference from our point of view because all we're doing is programming with them. So a vector can have any number of components. Often you talk about vectors in 4 dimensions or vectors in 3 dimensions. This is in 3 dimensions, this is in 4. That refers to the number of components. And we can perform operations on vectors just like we perform operations on individual numbers. And maybe you notice a similarity here. The reason it's coming up when it is that vectors look a lot like the kind of thing I might store in a one-dimensional array in a C program. So what can we do with vectors? Well, one operation is that we can perform addition. We can also perform subtraction. And when we add 2 vectors or subtract 2 vectors, we call that an element-wise operation. So if I want to compute v plus w, then what I want to do is, maybe what I'll do is I'll sketch the value of, here's v, and then here is w. I'll just sketch these out one on top of the other. If I want to add v to w, what I do is I just add the corresponding elements, and the result of adding those 2 vectors together is itself a vector in the same number of dimensions. You can only perform operations like this if the 2 vectors have the same size. It doesn't make sense to try and add a vector in 3 dimensions to a vector in 4. They have to have the same size or the operation just isn't defined. So in this case, v plus w would be 0, negative 3 plus 1 is negative 2, and 4 plus 1 is 5. So we can add them together. We could also subtract them. That is also an element-wise operation. Now, we might want to talk about being able to multiply vectors, but it turns out that in a linear algebra setting, which we don't care about theoretically, there really aren't very many occasions where you'd want to do a vector times vector operation that gives you a new vector, except maybe in 3 dimensions. You might have heard of something called a cross product, because we did that in a lab exercise, actually, so that might have been where you heard about it. It turns out that often multiplication, when we refer to vectors, actually refers to something called a dot product. And a dot product is not a vector. If I take the dot product of 2 vectors, I get a single number. So let's try and work that out. So what is v dot w? All right, so the way I'm going to do this, just like before, is I'm going to draw out v and w one on top of the other to allow myself to, that's a pretty ugly w, to allow myself to see the result without having to write too much. So v is 1, 2, 4, 5, and w is 3, 1, 0, 2. And to compute a dot product of 2 vectors, what you do is you pair the elements up position by position, so 1 and 3, 2 and 1, 4 and 0, 5 and 2. You take each pair, you multiply that pair together, and then you add up the product of each pair. So this would be v dot w would be 1 times 3 plus 2 times 1 plus 4 times 0 plus 5 times 2. I guess I should actually work that out, which should be 1 times 3 is 3 plus 2 plus, well, 0 plus 10, which equals 15. So the dot product of 2 vectors assuming those vectors have the same number of components, is a scalar value, a single number computed by multiplying together the pairs of elements and then adding up all of those, the products of each pair. All right, so that's vectors. I have to do more examples. Wait a minute. Okay, this is the same example again. Compute the dot product of these two. So v dot w. Okay, so what's v? Let's see. V is -1, -3. I've got to learn how to draw better threes. And then 4, and then w is 1, 1, and 1. All right, so we'll do the dot product. That would be -1 times 1 plus -3 times 1 plus 4 times 1, which ends up being -1 plus -3 plus 4, which actually comes to 0. Now, I can't help myself. We don't want to spend too much time on the theoretical implications of this, but it turns out that there is an interesting geometric parallel here, which is, or actually it's the opposite of a parallel, which is that if you have two vectors whose dot product comes to 0, it means those two vectors are perpendicular. They are orthogonal to each other. This is in 3 dimensions, so you might have to rotate around before we notice this, but there is a plane on which they form a right angle. Okay, that's great. That's one of the reasons why having dot products is important. And it actually shows up a lot, not only in engineering applications, but a lot of times it turns out if you ever heard about computer graphics or game design or things that involve graphics, it turns out a lot of computer graphics is just linear algebra. It's using vectors and matrices and things. In any case, we now know how to compute dot products. And my hope is that now that we know how to compute them, if you're asked to write code to compute them, sure, maybe in this course we don't cover what the implications of that are, but the code itself shouldn't be that complicated. We're taking two things that may be stored in arrays or something, then looping through it and computing products and adding up something into a single number. Okay, so we can compute dot products. What else do we have to learn about linear algebra? Well, there's also, we've seen this idea of a vector, which is sort of equivalent in a lot of ways to what we represent in a 1D array, and the natural question is, well, what about a 2D array? And so we have something called a matrix. Now, I know that not everybody taking 111 is also taking linear algebra, but those of you that are taking linear algebra probably know already that when you work with matrices, it tends to be pretty computationally intensive. Performing operations on matrices requires a lot of detail-oriented attention to adding up sums or whatever, because when you multiply matrices, when you work with matrices, there are a lot of numbers flying around, which makes it a perfect application for a computer program. So what is a matrix? And I'm not even going to pull any punches. I'll just admit it. Yes, it's a two-dimensional array of numerical values. That's the reason that we're going to be working with it. It also happens to be that if you talk about matrices in a linear algebraic context, you can talk about how they are formed out of vectors in a lot of ways. So, for example, it's often we often consider the column vectors of a matrix, which is we consider each column as a vector. We could also talk about things like row vectors. Well, we won't because it's a programming course. So here's a matrix M. It's got 2 rows and 3 columns. Here's a matrix Q. It's square. It's got 3 rows and 3 columns, but there's no requirement that a matrix be square. It can have any number of rows and any number of columns. So what can we do with matrices? Oh, I guess I have to talk about this. One example of a special matrix that shows up in a lot of contexts and that likely you've seen a lot of if you're taking Math 110 is something called the identity matrix. The identity matrix is always square. And so we write out its name using a notation like I4 or I5. And because it's square, it's got 4 rows and 4 columns. And what's the distinguishing characteristic of the identity matrix is that along the forward diagonal, so starting at the top left down to the bottom right, if we number our rows and columns, and in linear algebra, we usually start our numbering at 1. If we number our rows and columns, every place where the row number and column number are equal, we set that to a 1. Everywhere else, we set the value to a 0. And if you've seen the identity matrix before, you might know that one of the special characteristics it has is that if you multiply something by the identity matrix, you get the original matrix back again. The identity matrix has no effect on something if you multiply it. But whatever, what's this whole multiplication business anyway, Bill? Well, I don't know. We'll have to find out ourselves. So here's an example of an operation we can do with matrices. We can add 2 matrices together. And just like with vectors, adding 2 matrices is an element-wise operation. We can only add 2 matrices if they are the same dimension, same number of rows, same number of columns. So what is P plus Q? We just add the elements element-wise. So the top left element in P is added to the top left element of Q. So that's -1, 1 plus 0 is 1, 2 plus 6 is 8, 6 plus 1 is 7, 10 plus 2 is 12, 17 plus 2 is 19, -2 plus 0 is -2, 0 plus 1 is 1, -3 plus 0 is -3. Hopefully that wasn't too much of a surprise. I wonder if we could do that with a loop. Well, we probably could. So we can perform the same style of addition and subtraction operations on matrices as we can with vectors. We can also multiply vectors and matrices by scalar values. So I could ask you, what is the value, I'm not going to use 2, what's the value of 5 times Q? And the answer is, it will be a matrix that consists of every element of Q multiplied by 5. And the same is true of vectors. You can multiply a vector by a scalar. But just like vectors, when we talk about multiplication, things become a little bit more complicated. Multiplying two matrices is not generally done element-wise. There are certain advanced scenarios where you actually would want to do an element-wise multiplication. But if we talk about matrix multiplication, if I ask you for the product P times Q, I am not asking to take this element and multiply it by this one, take this element and multiply it by this one. I'm asking for something a great deal more complicated and probably pretty confusing at first. I'm talking about something called matrix multiplication. So if I have an n by n matrix and I have an n by k matrix, and you can imagine this is why they have a separate course to talk about this sort of thing. The key thing with matrix multiplication is that unlike other types of multiplication, if I compute a times b, that is not necessarily going to be the same as if I compute b times a. And additionally, it's possible, if I have two matrices, that it isn't possible to multiply those matrices together, that it's not allowed. Okay, but what do we do with this? This is a great formula, for example, if you're implementing an assignment, but what does matrix multiplication really mean? This definition is a lot. We don't want to have to give a 2-hour lecture on matrix multiplication, so I guess in a programming course, the only question we should ask is, okay, how do we do matrix multiplication? And there is just a lot to digest. I don't know. You know, often when I don't know what to do, when I feel lost, I ask myself, what would Bill Bird do in this situation? And then I just do that thing. I found that that's actually worked for me a lot in life. So, okay, I don't know what to do with matrix multiplication, but you know what would probably help? I know what Bill Bird would do. He would use a diagram. Okay, so if we choose the right kind of diagram, maybe that will do the work for us. So here is the way that I do matrix multiplication. I start by drawing out my matrix P. I make a copy of it. 0, 1, 2, 6, 10. Okay, so there's P. We'll label it. And then I take my matrix Q and I put it corner to corner with P. So I put Q above and to the right. So I'm going to put Q right there. Okay, so there's my copy of Q. And then I stare at this. Actually, I'm going to straighten this line out a bit. And then I stare at this diagram. And remember, if we use diagrams effectively, the diagram does the work for us. So I stare at this diagram, and of course, the very first thing I notice, if you take any courses in fine arts or something, I think they talk about this, I notice in this conspicuous negative space, I think the term is, it seems like there's something missing. This really needs something, this empty space here. Okay, so, it looks like it's exactly big enough for a new matrix, a matrix of 3 rows and 3 columns, filling that entire void left between P and Q. Okay, then the question is, how do I fill it in? I've got this new matrix, 3 rows, 3 columns. What's the value of each element? So for example, what's the value of this element here? And I notice this element happens to be at the intersection of this line and this line. Well, that's convenient. And I ask myself, okay, so I've got 3 numbers in a row over here. I've got 3 numbers in a row over here. Actually, wait, where have I seen numbers in a row before? Oh yeah, that's right, vectors. So I have 2 vectors, and I want to compute their dot product, and that gives me 1 number. So if I have these 2 vectors and I compute their dot product, I get 1 number. Well, that's neat. Let's go back and look at our matrix again. Okay, so here, I'm at this element. I've got 3 things here, 3 things there, but what I want here is 1 number. That sounds like a job for a dot product. And it turns out you can compute matrix multiplication using a whole bunch of dot products. What you do is for each element, you draw a line upwards and you draw a line over to the left. And you take the vectors that those lines intersect and you take the dot product of them. So the dot product of these two vectors is -1 times 0, okay, that's 0, 1 times 1, okay, so that's 1, plus 0 times 2, so this entry is 1. What about this entry here? That's at the intersection of this line and this line. Okay, so that's 0 times 0 is 0, 2 times 1 is 2, 1 times 2 is 2. Add those up and I get 4, so this entry is 4. Okay, what about this entry here? That's the intersection of this line and this line. Okay, so that would be 6 times 0 is 0, 1 times 2 is 2, 2 times 1 is also 2. Oh, whoops, actually I copied this matrix down incorrectly. This is a 0. It's that thing. Okay, so we'll try that again. 6 times 0 is 0, 2 times 1 is 2, 2 times 0 is 0, so that's a 2. What about this entry? Okay, let's take a look. All right, so it's these two things. -1 times 6 is -6. 1 times 10 is 10. -6 plus 10 is 4. Okay, what about this entry? That's this by this. All right, 0 times 6 is 0. 2 times 10 is 20. 1 times 17 is 17. So I add those together and I get 37. And then finally this entry here. Okay, 6 times 6 is 36. 2 times 10 is 20. That brings me to 56. 0 times 17 is 0, so I'm stuck at 56. And then this one here, -1 times -2 is just 2. And then 1 times 0, 0 times 3, so I'm stuck at 2. This entry here is this by this, so I have 0 times -2 is 0. 2 times 0 is 0. 1 times 3 is 3. And then finally, this. So 6 times -2 is -12, and then 2 times 0 is 0, 3 times 0 is 0, so I just have -12 there. All right, so the diagram helped me a lot there. Having a diagram made it easy to know when I fill in each entry what numbers do I look at, and it helped me understand how big the result was. But we might notice this ominous word up here, attempt to compute. Well, that's not very nice. I don't think the question doesn't seem to believe in me very much. But it turns out that what that's actually saying is that in some cases, if you have two matrices, it might not be possible to multiply them together. And we'll see an example of that in a minute. First, we'll try this one. Attempt to compute p times q based on these definitions. Okay, so I copy down p, 0, 1, 2, 17, 6, 10. All right, so there's p. And then there's q. I guess I should have labeled on my previous example. This matrix down here, this is p times q. It's result. Okay, so q, -1, 0, 1, 2. Make sure I copy that down correctly this time. Okay, so now I've got that negative space between p and q. And I notice that it's exactly 3 rows high and 2 columns wide. So my result, pq, will be 3 rows and 2 columns. Okay, so we compute it. We start here. That's this by this. So -1 times 0 plus 1 times 1, that's just going to be 1. Here's 0 times 0 plus 1 times 2 is 2. -1 times 2 is -2, and then 1 times 17 brings me to positive 15. 0 times 2 is 0. 17 times 2 is 34. Down here, I have this line by this line. So that would be -1 times 6 is -6. 1 times 10 is 10, so I get 4. And then 0 times 6 is 0. 10 times 2 is 20. All right, so I've computed p times q, the matrix product p times q. And because of the way we're doing this, maybe you'll notice that if I put q, if I interchange the arguments and q comes first, then it'll appear differently on my diagram, and the result I get, if I'm allowed to compute that result, will be different. Let's move on to the next example. Okay, attempt to compute p times q based on the definitions. Okay, so we copy that in. So let's see, p has 4 rows and 2 columns. All right, there it is. And q has 3 rows and 4 columns, 0, 1, 1, 2. All right, so if I'm allowed to compute this, the result will have 4 columns and 4 rows. Okay, let's get started. So I start by trying to compute this element here. I have to take the dot product of this thing and this thing. And remember what I said about dot products earlier. You can only take the dot product of two vectors if they are the same size. And in this case, I've got 2 elements over here and 3 elements here. So I can't compute a dot product. And it turns out that that means I can't compute this matrix product either. So these two matrices can't be multiplied. The dimensions don't match up. In general, the dimensions, you can only multiply two matrices if the number of columns in the first matrix matches the number of rows in the second matrix. That is the rule, but from my end, the only way I ever figured that out is by drawing it out and deciding whether the dot product made sense. And in this case, it doesn't. So I'll write, we can't do it. All right, what about this though? So I've swapped P and Q. Well, and I said before that P times Q and Q times P are different things. What if I try to compute this matrix product? Okay, so 0, 1, 1, 2, 6, -1, -2, 0, 10, 10, 10, 10, okay? And then Q is -1, 0, 1, 2, 6, 10, 0, -6. All right, so here's P and here's Q, and my result PQ would then have 3 rows and 2 columns. Okay, the question should then be, can I do this? And I notice that if I'm standing right here, there's 4 things above me and 4 things to my left. So it looks as if the dot product works out. So we'll go through and compute each element. Okay, -1 times 0 is 0. 1 times 1 is 1, plus 6 looks so ugly. 1 times 1 is 1. 6 times 1 is 6, so we're at 7 now. 2 times 0 is 0, so we've just got a 7. This 2 also looks ugly. We'll fix that. Over here, 0 times 0 is 0. 2 times 1 is 2. 10 times 1 is 10, plus the 2 is 12. And then that's plus -6 times 2, which is -12, brings us back down to 0. Here we've got -1 times 6 is -6, plus -1 is -7, plus -12 is -19. 0 times 6 is 0. 2 times -1 is -2. 10 times -2 is -20. So we're at -22 now. Plus 0 is just -22. And then down here, -1 times 10 is -10. Plus 1 times 10 brings us to 0. Plus 6 times 10 is 60. Plus 0 times 10, so we're at 60. And then finally, this entry here, we've got, let's see, 0 times 10 is 0. 2 times 10 is 20. Plus 10 times 10 is 100. That brings us to 120. Plus -6 times 10 is -60, which brings us back down to actually just 60 again. And that is how you multiply a matrix.